Imagine you're constructing a house. You lay the foundation, put up the frame, run the electrical wires, and install the plumbing. It's a process that takes months, maybe even years. Now, picture driving by that same plot of land the morning after the concrete is poured, only to find a fully finished mansion, complete with furniture and decorations, standing there as if it had always existed. That's the kind of shock astronomers felt when the James Webb Space Telescope peered into the universe's earliest days. Instead of finding the primitive, slowly forming galaxies they expected, JWST revealed mature, chemically evolved galaxies already present just a few 100 million years after the Big Bang. These weren't just isolated oddities, either. Across hundreds of objects and dozens of independent studies, the same story kept repeating. The universe's timeline, as we understood it, simply didn't add up. It was as if the factories were running before anyone had even approved the blueprints. What follows is a summary of 3 years' worth of discoveries from the most advanced telescope ever launched, combined with data from ray observatories and ground-based instruments that together span over 11 billion years of cosmic history. The evidence is mounting that our standard model of cosmology is either missing a crucial piece or is fundamentally flawed. It all began with a single image, snapped from 1 million miles away, capturing a patch of sky no bigger than a grain of sand held at arm's length. On July 12, 2022, NASA released the first full-color images from JWST. The target was a tiny region centered on the galaxy cluster SMO 723. In that image, thousands of galaxies appeared, their light stretching back more than 13 billion years. Within hours, astronomers worldwide were downloading the raw data, and within days, some began noticing objects that simply didn't fit any existing theory. JWST was a quarter-century in the making, with a price tag of about $10 billion. Its main mirror, made up of 18 gold-coated hexagons, spans over 6 meters. The whole assembly sits behind a sun shield the size of a tennis court, which was folded up for launch, and then carefully unfurled over 2 weeks as the telescope drifted to its permanent home at the second Lagrange point, about 1.5 million kilometers from Earth. There it orbits in sync with our planet, always keeping its back to the sun. The telescope launched on Christmas Day 2021 atop an Ariane 5 rocket from French Guiana. It arrived at L2 a month later, and then spent 6 months being calibrated. Engineers painstakingly aligned the mirror segments to within a fraction of a wavelength of infrared light. One by one, the instruments came online: NENARCAM for near-infrared imaging, NAR-SPEC with its micro-shutter array capable of observing over 100 objects at once, and MIRE for mid-infrared. Each was designed to see light stretched by the universe's expansion, shifting visible wavelengths into the infrared. JWST's main mission was to observe the first galaxies that formed after the Big Bang. For decades, cosmologists had built models predicting what those galaxies should look like: small, faint, simple clumps of hydrogen and helium, maybe 100 million times the mass of our Sun at most. These predictions came from the Lambda CDM model, the reigning theory of cosmology for the past 25 years. According to Lambda CDM, the universe is made up of about 5% ordinary matter, 27% dark matter, and 68% dark energy. It predicts that galaxies form slowly, growing through mergers over billions of years, starting as tiny seeds and gradually combining into the massive structures we see today. The first deep field image from JWST was supposed to confirm this picture. Instead, it showed bright, compact sources at distances corresponding to the universe's first few 100 million years. They were too bright, too massive, and too well structured. Early estimates suggested their masses far exceeded anything the models allowed. Astronomers double-checked their calculations, but the results held up. At first, no one panicked. New telescopes always produce surprises in their first data. calibration errors are common, and the methods used to estimate distances and masses, especially at such extreme distances, are full of assumptions that might not hold up. The standard advice was to wait for spectroscopic confirmation before drawing any big conclusions. The anomalies were noted and flagged for follow-up, but the follow-up data didn't make the problem go away. Over the next several months, as more surveys came online and more regions of the sky were observed, the anomalies multiplied. They showed up in the deepest surveys, in the widest, in different parts of the sky, using different instruments. Teams kept finding the same thing: galaxies in the early universe that were too massive, too bright, and too complex to exist according to any version of the standard model. 2020, a team led by Ivo Labbé at Swinburne University in Australia published a paper that turned these scattered anomalies into a full-blown crisis. The Cosmic Evolution Early Release Science Survey (CRS) had identified 6 galaxy candidates at high redshift, each apparently exceeding 10 billion solar masses. That's 10 billion times the mass of our Sun, packed into galaxies that formed when the universe was less than 500 million years old. To grasp why this is such a problem, consider what 10 billion solar masses means. Our own Milky Way contains about 200 billion stars, and has been assembling for over 13 billion years. These 6 candidates seem to have accumulated a significant fraction of that mass in less than 1/20th the time. The analogy that spread through astronomy departments was blunt. Finding these galaxies was like discovering a skyscraper in a neighborhood where the concrete was poured yesterday. Lab's team used NIRCam photometry to estimate the redshifts and stellar masses. The galaxies appeared at redshifts between about 7 and 11, corresponding to the first 300 to 700 million years after the Big Bang. At those epochs, the standard model predicted galaxies of maybe 100 million solar masses. The CRS candidates were 10 to 100 times more massive than the upper limit of any prediction. Mike Boylan-Colchin, a theoretical astrophysicist at the University of Texas at Austin, took the CRS results and pushed them further. His 2023 paper in Nature Astronomy framed the issue as a stress test for the Lambda CDM model. He calculated something remarkable. If you took the mass estimates at face value, these 6 galaxies collectively contained more stellar mass than the universe should have been able to produce at that time. It was as if someone had spent more money than existed. The impact of Boylan-Colchin's calculations was immediate and widespread. Headlines started calling these impossible galaxies. News outlets ran stories suggesting the Big Bang itself was in jeopardy. Though that wasn't quite accurate. The real issue wasn't with the Big Bang as a concept, but with everything that happened after it. The standard timeline for how galaxies and stars should have formed was suddenly under intense scrutiny. Lab's team and others were careful to acknowledge the uncertainties. The redshifts they used were based on photometric estimates, which are essentially educated guesses made by measuring how bright an object appears through different filters. This method can be thrown off by dust, unusual stellar populations, or calibration errors, without spectroscopic confirmation, which involves splitting the light into its component wavelengths and looking for specific chemical fingerprints. The distances and masses could be off. A galaxy that looks like it's at redshift 10 might actually be much closer, its colors mimicking a more distant object for reasons we don't fully understand. The astronomy community responded with healthy skepticism. Many argued that the masses couldn't possibly be right. After all, JWST was a brand new instrument, and its calibration was still being refined. No one had ever tested photometric redshifts at these distances against spectroscopic measurements, simply because no previous telescope could reach that far. So, the community waited for the next step: spectroscopy. When the spectroscopic data started coming in, the story became more complicated, not less. Teams using JWST's NARSpec instrument targeted the CRS galaxies one by one, breaking their light into spectra and searching for emission lines that would nail down their exact red shifts. The results were mixed, and the emerging picture was messier than the headlines had suggested. First, the critics were partly vindicated. Early in JWST's operations, NARCam's calibration had systematic errors. The photometric pipeline overestimated the brightness at certain wavelengths, which in turn inflated the inferred stellar masses. When the data was reprocessed with improved calibration, some of the mass estimates dropped, sometimes by a lot. Second, some of the redshift estimates shifted. A few of the candidate galaxies turned out to be closer than initially thought, meaning they had more time to form. Others, however, were confirmed at their original, extreme distances, though with revised masses. The 6 galaxies that had sparked so much debate were no longer all sitting at 10 billion solar masses. The media, always hungry for drama, quickly lost interest. Galaxies slightly less massive than previously thought doesn't make for a gripping headline. But for astronomers, the story was far from over. Even after all the corrections, recalibrations, and spectroscopic confirmations, the galaxies at high redshift remained significantly more massive than the lambda CDM model could account for. The numbers had been shaved down from impossible to still inexplicable. Boylan-Kolchin's core calculation still stood. The early universe contained more stellar mass than the standard model's budget allowed at those epochs. It was like discovering someone had spent more money than existed in the bank, just not quite as much as first thought. In 2025, a group working on the Renaissance simulations, a suite of sophisticated computer models of galaxy formation, offered another possible way to reduce the tension. They suggested that if the first generation of stars followed a top-heavy initial mass function, meaning a much larger proportion of massive stars compared to what we see today, the inferred masses from JWST's photometry would drop by about a factor of 10. Massive stars are much brighter per unit mass, so you need fewer of them to produce the same amount of light. This was a physically plausible idea. If the earliest stars were mostly heavyweights, then what looked like 10 billion solar masses of ordinary stars might actually be just 1 billion solar masses of very bright ones. A factor of 10 reduction sounds like it would solve the problem, but it didn't. Even at 1 billion solar masses, these galaxies at redshifts above 10 were still far more massive than hierarchical assembly models predicted. The top-heavy IMF made the crisis less severe, but it didn't make it go away. This pattern, where a correction reduces a crisis from dramatic to merely persistent, is common in science. A bold claim grabs attention. A correction follows, the public loses interest, but the underlying anomaly remains, quietly waiting for someone to explain it. Some astronomers started calling this the overcounting scandal. It didn't prove the crisis was fake, it proved the crisis was real, just less photogenic than the first round of papers had suggested. So the question shifted. If these galaxies are real, and their masses are genuinely higher than predicted even after every reasonable correction, then something about how stars formed in the early universe must have been fundamentally different from what the models assumed. The question was no longer whether JWST had found something strange. The question was how the early universe managed to turn gas into stars with an efficiency that no known physics could explain. Star formation efficiency is one of those quietly crucial numbers in astrophysics. It measures what percentage of the available gas in a galaxy actually gets converted into stars over a given period. In the modern universe, that number hovers around 10%. About 90% of the gas in a typical galaxy never becomes a star at all. This low efficiency is well understood. Stars form inside dense clouds of molecular gas, but as soon as the first stars ignite, they push back. Radiation pressure from hot young stars blows gas outward, stellar winds carve out cavities. And when the most massive stars explode as supernovae, they blast away the remaining gas. This feedback cycle limits how much gas can be turned into stars in any single episode. Turbulence within the gas clouds adds another break, preventing large-scale collapse. Across galaxies of all sizes, at all distances, in all environments, the 10% efficiency number seems almost universal. And then JWST found the blue monsters. These are a class of galaxies identified in the CERAS and JWST surveys at redshifts above 10, corresponding to the first 400 million years after the Big Bang. They're tiny, just a few hundred parsecs across, which is only a few thousand light years. For comparison, the Milky Way is about 100,000 light years wide, but their ultraviolet output is off the charts. Their UV spectral slopes, measured by the Greek letter beta, are extremely steep, indicating populations of young, hot stars with almost no dust to obscure them. They're blue because they're furiously producing massive, short-lived stars that burn through their fuel in just a few million years. The stellar masses inferred for these blue monsters range from 100 million to 1 billion solar masses. Given their compact sizes and the available gas supply at their epochs, the star formation efficiency required to produce these objects exceeds 50%. Some early estimates from CERAS data even pushed toward 100%. Every atom of available gas becoming a star. No known physics achieves this. The feedback mechanisms that limit efficiency to 10% today should have been even more effective in the denser, hotter early universe. And yet, these galaxies converted gas to stars at 5 to 10 times the expected rate. No one has yet identified what process could have made this possible. The blue monsters raised the stakes of the JWST anomalies from a question of mass to a question of mechanism. It was no longer enough to say the early galaxies were surprisingly large. Now the question was how. The discovery of the blue monsters didn't just challenge our understanding of how much mass could be assembled so quickly. It forced astronomers to confront the possibility that the very rules of star formation might have been different in the universe's infancy. The question shifted from how did these galaxies get so big to how did they get so big, so fast, and with such efficiency? The numbers just didn't add up. In the modern universe, star formation is a slow, inefficient process, throttled by feedback from the very stars it creates. But in these early galaxies, it seemed as if the brakes were off and the gas was being converted into stars at a rate that defied every known mechanism. And the blue monsters weren't the only evidence that something fundamental had changed. JWST also detected chemical signatures in the early universe that, according to standard models, should have taken billions of years to appear. The most striking example came in January 2024, when a team led by Stefano Carniani confirmed the redshift of a galaxy known as JWST GS420 using about 10 hours of NENR spectroscopy. The redshift came in at 1432, making it the most distant spectroscopically confirmed galaxy ever observed, seen as it existed just 290 million years after the Big Bang. To put that in perspective, if you compressed the entire history of the universe into a single calendar year, with the Big Bang at midnight on January 1, JWST GS420 would appear on January 8. This galaxy existed during what cosmologists call the cosmic dawn, the era when the first sources of light were just beginning to flicker on in a universe that had been dark since recombination. JWST GS420 is small by modern standards, spanning about 1/600 light years, but it's remarkably well defined for its age. Its luminosity and inferred stellar mass both exceed what the lambda CDM model predicts for objects at this redshift. But the real surprise wasn't its size or brightness, it was what Carniani's team found in its spectrum: oxygen. At 290 million years after the Big Bang, the universe was supposed to contain almost nothing but hydrogen and helium, the two elements forged in the first few minutes after the Big Bang. Heavier elements, what astronomers call metals, regardless of whether they're actually metallic, are produced inside stars through nuclear fusion. When those stars die, they scatter these elements into the surrounding gas via stellar winds and supernova explosions. The next generation of stars forms from this enriched gas, and the cycle repeats, gradually increasing the universe's chemical complexity. Oxygen is the third most abundant element in the cosmos today, after hydrogen and helium. It's produced primarily in the cores of massive stars, those at least 8 times the mass of our Sun, through the carbon-nitrogen-oxygen fusion cycle. These massive stars live fast and die young, typically burning out in just 5 to 10 million years. But to produce detectable oxygen in a galaxy, you need multiple generations of massive stars to live, die, and enrich the interstellar medium with progressively more oxygen-rich material. The standard timeline for this process allows for hundreds of millions of years at minimum. Finding oxygen at 290 million years after the Big Bang compresses that timeline almost to the breaking point. Some theoretical models can barely accommodate it, but only by invoking extremely massive first-generation stars that formed immediately and died within a few million years, enriching the gas for a rapid second and third generation. But these models require exactly the kind of high star formation efficiency that the blue monsters already demonstrated was problematic, and they require it even earlier. JWST 40 held the distance record for nearly 2 years, becoming one of the most studied objects in extragalactic astronomy. Teams analyzed its structure, its spectral energy distribution, its chemical abundances. Each new analysis added detail to a picture that remained stubbornly difficult to explain within the standard framework. Then, in January 2026, the record was broken by another galaxy that was even harder to explain. The galaxy, dubbed MAM Z14, was confirmed at a redshift of 14.44, just edging past JWST 40. The light from MAM Z14 left its source about 280 million years after the Big Bang, only 10 million years earlier than the previous record holder. At these redshifts, that's a blink of an eye. What made MAM Z14 remarkable wasn't just its distance but its size, or rather its lack of size. While JWST 14 ZU measures about 1/600 light-years across, MAM Z14 is only about 240 light-years wide, almost 7 times smaller. Here were two galaxies, existing at essentially the same moment in cosmic history, separated by an insignificant gap in time. Yet one was nearly an order of magnitude larger than the other. This was not what the models predicted. The prevailing theories of early galaxy formation assumed that the first galaxies would share broadly similar properties, forming from similar initial conditions under similar physical processes. The cosmic dawn was supposed to be a relatively uniform period, with the first structures emerging from nearly identical seeds scattered by quantum fluctuations in the early universe. Finding two galaxies at redshift 14 with such wildly different sizes shattered that assumption. The diversity of the earliest galaxies implied that multiple formation pathways were already operating when the universe was barely 280 million years old. Whatever process built JWST 40 into a 1/600 light-year structure didn't operate the same way for MAM Z14, and whatever compressed MAM Z14 into a 240 light-year package didn't affect its neighbor at nearly the same epoch. This matters because it means the earliest moments of galaxy formation were more complex than any model anticipated. A single explanation for the anomalies, whether top-heavy stellar populations, unusual gas accretion, or something else, would need to account for objects being dramatically different from each other, spanning a huge range of sizes at the same epoch. The problem wasn't just that the early universe made galaxies too fast, it was that it made several kinds of galaxies too fast, through mechanisms that produced a range of outcomes the models couldn't reproduce. Z14 is still being studied. Its compactness raises questions about its stellar density, its formation mechanism, and whether it contains the same chemical signatures as JWST Z14. Spectroscopic analysis is ongoing, and the results will either deepen the diversity problem or reveal some common thread connecting the two record holders. To appreciate the scale, 240 light years is roughly the distance from our Sun to Arcturus and back, 60 times over. That's the entire width of a galaxy. A galaxy that formed when the observable universe was smaller than the distance between the Milky Way and the Andromeda galaxy today. But JWST wasn't done pushing boundaries. Before it could reach even deeper into the cosmic dawn, it had already found something closer in time, but far more disturbing in its implications. A black hole at the center of a galaxy, just 470 million years after the Big Bang, weighing as much as every star in its galaxy combined. The galaxy in question is known as UHZ1, and its discovery added a new layer of mystery to the early universe. UHZ1 sits at a redshift of about 10·1, which places it just 470 million years after the Big Bang. What's remarkable isn't just its age or distance, but what lies at its heart. A supermassive black hole whose mass rivals that of all the stars in its host galaxy combined. JWST didn't spot UHZ1 directly. Instead, this galaxy is located behind one of the most massive galaxy clusters known, Abell 2744. The immense gravity of this cluster bends the fabric of space itself, acting as a natural magnifying glass, a phenomenon called gravitational lensing, first predicted by Einstein. This lensing effect amplified the light from UHZ1 by about a factor of 4, making it visible to JWST's sensitive infrared cameras. But identifying the galaxy was only the first step. The real breakthrough came from NASA's Chandra X-ray Observatory, which has been orbiting Earth since 1999. Chandra focused on the same patch of sky for over 2 weeks, collecting faint X-ray photons from an object whose light had traveled more than 13 billion years to reach us. Each photon carried information about conditions in a galaxy that existed when the universe was just 3% of its current age. The X-ray signal told a clear story. UHZ1 harbored an active galactic nucleus, meaning a supermassive black hole was feeding on surrounding material, heating it to temperatures that produce X-rays. This alone would be notable at such an early epoch. But the real shock was the mass estimate. The black hole at the center of UHZ1 weighs in at about 40 million times the mass of our Sun. That's a large black hole by any standard. But what's truly extraordinary is the ratio in the local universe. Supermassive black holes typically account for about 0.1% of their host galaxy's total stellar mass. The black hole at the center of the Milky Way, for example, is about 4 million solar masses. While the galaxy itself contains hundreds of billions of stars, in UHZ1, the black hole's mass is not a tiny fraction. It's somewhere between 10% and 100% of the total stellar mass. That's 100 to 1,000 times higher than what we see in nearby galaxies. This ratio simply can't be produced by the standard model of black hole growth. According to conventional wisdom, supermassive black holes start as the remnants of massive stars, so-called stellar mass seeds, weighing perhaps 100 times the mass of our Sun. These seeds then grow by accreting gas and merging with other black holes. But there's a speed limit, the Eddington limit. This is the point where the radiation pressure from infalling material pushes back against further accretion, effectively capping the growth rate. At the Eddington rate, a 100 solar mass seed would need well over 600 million years to reach 40 million solar masses. UHZ1's black hole did it in 470 million years. And that's only if it started growing the instant it formed, which is unlikely. The numbers just don't work. The team led by Priyamvada Natarajan at Yale University published their findings in Nature Astronomy in late 2023. Their paper didn't just report a big black hole. It reported a black hole that couldn't have formed through any known growth mechanism in the available time. If it couldn't have grown that fast, it must have started out much bigger than any stellar mass seed. This meant the origin story for supermassive black holes needed a complete rewrite. The standard story goes like this: a massive star, maybe 20 or 30 times the mass of our Sun, burns through its fuel and collapses, leaving behind a black hole of about 100 solar masses. Over hundreds of millions of years, this black hole drifts toward the center of its galaxy, merges with others, and accretes gas. Growing slowly, after billions of years, it becomes the supermassive black hole we see at the centers of modern galaxies. This is called the light seed scenario, and it's been the default explanation for decades. UHZ-1 broke that model. 40 million solar masses in 470 million years, starting from a 100 solar mass seed, is mathematically impossible at the Eddington rate. Even if you allow for brief periods of super-Eddington accretion, where the black hole temporarily exceeds its theoretical feeding limit, the numbers still don't add up. Natarajan's team proposed an alternative, the direct collapse black hole model, sometimes called the heavy seed scenario. In the very early universe, before any stars had formed, vast clouds of pristine gas existed, containing no metals at all. Metals are crucial for star formation because they help gas cool efficiently. Without metals, cooling is inefficient and the gas cloud doesn't fragment into smaller pieces the way metal-enriched gas does. Instead, the entire cloud can collapse under its own gravity. If the cloud is massive enough and doesn't fragment, the result isn't a star, it's a black hole. In this scenario, black holes start out much heavier at 10,000 to 100,000 solar masses. A heavy seed of 100,000 solar masses, accreting at the Eddington rate from the moment it forms, could reach 40 million solar masses in the time available before UHZ-1's epoch. The math finally works. But the heavy seed model comes with a radical implication. It flips the usual relationship between black holes and galaxies. In the standard picture, galaxies form first and black holes grow inside them. In the direct collapse scenario, the black hole forms first, and the galaxy assembles around it from leftover gas and material. The black hole isn't a passenger in its galaxy, it's the foundation. This would explain the odd mass ratio in UHZ-1. If the black hole formed before the galaxy, and the galaxy is still assembling, then at early times the black hole would dominate the total mass. Over billions of years, as more gas falls in and more stars form, the galaxy would eventually outgrow the black hole, and the ratio would fall to the 0.1% we see in the local universe. The ratio isn't anomalous, it's a snapshot of a galaxy still under construction. Natarajan had been developing the heavy seed theory for over 15 years, long before JWST launched. The telescope didn't inspire the theory. It provided the first observational evidence that matched its predictions. UHZ-1 is exactly the kind of object the direct collapse model expects, an oversized black hole sitting inside an undersized galaxy at high redshift, and JWST found more than just one. It uncovered an entire population of objects that might be the cocoons where this process played out. Compact, red sources scattered across every deep field the telescope observed, matching nothing in any previous catalog or simulation. Starting in 2022, as astronomers sifted through JWST's deep field images, they began to notice a peculiar population of objects. These were small, red, and either unresolved or barely resolved, even with JWST's sharp infrared vision. Their spectral energy peaked at longer wavelengths, and they appeared in surprising numbers across every patch of sky the telescope surveyed. At first, The assumption was straightforward: these must be distant galaxies, their light reddened by dust or stretched by the expansion of the universe. Astronomers flagged them for follow-up and moved on to other priorities. But as the months passed and more data poured in, these little red dots, as they came to be called, refused to fit into any familiar category. By 2024, teams had begun spectroscopic follow-up, and the results were unexpected. The spectra of these objects showed features consistent with active galactic nuclei, meaning each one seemed to harbor a supermassive black hole that was actively feeding. But there was a catch: their sizes were all wrong. Each measured less than 1,000 light-years across. For comparison, most galaxies hosting active supermassive black holes in the local universe are tens of thousands of light-years wide. By 2025, astronomers had cataloged 341 of these little red dots across multiple surveys. They clustered between redshifts 5 and 10, corresponding to a period from about 500 million to 1 billion years after the Big Bang. Even more puzzling, their number density, the number of active black holes per unit volume, was about 50 times higher than any existing model predicted. And then, below redshift 5, they simply vanished. No similar objects exist in the nearby universe. No known type of galaxy, quasar, or compact object matches their properties. It was as if an entire population of objects had appeared, persisted for a couple of billion years, and then disappeared without leaving any descendants. This alone would have made the little red dots one of the most intriguing discoveries in extragalactic astronomy. But the mystery deepened when the JWST survey, which was analyzing these objects in detail, found something even stranger. In one particular little red dot at redshift 355, they detected a Balmer break, a sharp drop in brightness at a specific wavelength caused by hydrogen atoms absorbing photons of certain energies. Balmer breaks are well understood features in spectroscopy, used for decades to determine the age, temperature, and composition of stellar populations. But this Balmer break didn't match any known template. It wasn't like a typical galaxy, nor did it resemble the spectrum of a standard active galactic nucleus or quasar. The spectral signature dropped off so sharply that the team described it as a cliff, a feature that no existing model could reproduce. They named it accordingly, the cliff at redshift 355. It was a spectral fingerprint that belonged to an object for which no theory existed. At this point, the little red dots had become a full-blown puzzle. What could they be? Joel Leja, an astrophysicist at Penn State, proposed a bold explanation in September 2024. He suggested that the little red dots weren't galaxies at all, but something entirely new, a black hole stars. In this scenario, a massive cloud of pristine gas in the early universe collapses directly into a black hole, following the heavy seed mechanism described for UHZ-1. But instead of all the surrounding gas being immediately accreted or blown away, a substantial envelope of gas remains around the newborn black hole. The black hole heats this envelope from within, causing it to glow across a broad range of wavelengths. From a distance, the object looks like a galaxy, compact, red, and as luminous as billions of stars, but it's actually a single black hole wrapped in a cocoon of hot gas. This idea could explain several of the little red dots' properties at once. Their extreme compactness would make sense. There's no galaxy, just a gas cocoon that could be as small as a few hundred light-years across. The strange spectra, including the cliff, could be interpreted as the emission from a heated gas envelope, rather than a population of stars. No stellar template would match because there are no stars, just gas. The Balmer break would be produced by hydrogen in the cocoon, not in the atmospheres of billions of stars. Even the vanishing act could be explained. Gas cocoons are temporary. Over time, the black hole either accretes the remaining gas or blows it away with its radiation. Once the cocoon dissipates, What's left is a naked supermassive black hole, invisible at optical and near-infrared wavelengths. The little red dots didn't die, they simply shed their cocoons and went dark. If Leja's hypothesis is correct, the 341 little red dots in JWST's data represent a phase of black hole evolution that nobody had ever theorized before. An entire category of astrophysical object, visible only during a brief window of cosmic time, had been completely absent from every model and textbook. The implications are profound. If these are black hole cocoons, then supermassive black holes in the early universe were even more common than the already elevated numbers suggest. Every little red dot would be a direct collapse black hole in its chrysalis stage. Leja's idea remains unconfirmed, but it makes specific predictions about emission line ratios and spectral shapes that can be checked against the data. Confirmation would require ruling out every alternative explanation, and several still compete for attention. But the black hole star idea wasn't even the most radical proposal on the table. Another team had been working on a theory that went further, suggesting that some of JWST's most distant objects might not be galaxies or black hole cocoons at all, but individual stars of almost unimaginable mass, powered by a fuel source that physics has never directly observed: dark matter. This concept, known as dark stars, was first proposed by Catherine Fries at the University of Texas at Austin back in 2007, long before JWST launched. The name is a bit misleading. They're not dark at all, but among the brightest objects in the universe. The dark refers to their fuel source. In standard stellar physics, stars shine by fusing hydrogen into helium. Dark stars, on the other hand, would be powered by the annihilation of dark matter particles inside a primordial gas cloud. Dark matter makes up about 27% of the universe's total energy content, but it's never been directly detected. Its gravitational effects are everywhere. Galaxies rotate too fast for their visible matter. Clusters hold together more tightly than their luminous mass can explain, and something invisible is doing the work. Fries's proposal was specific in the earliest epoch of the universe. Dense halos of dark matter would have collected around clumps of primordial gas. If dark matter consists of particles that can annihilate when they collide, those annihilations would release energy into the gas cloud, heating it and preventing it from collapsing into a normal star. Instead, you'd get something enormous. A single star with a mass up to 1 million times that of our Sun, as luminous as an entire galaxy. And here's where JWST comes in. When astronomers point the telescope at the most distant objects, they see bright, compact sources at extreme redshifts. They assume these are galaxies containing millions or billions of stars. But a dark star of 1 million solar masses would look almost identical in JWST's imaging data. Same brightness, same compactness, same redshift. You can't tell them apart with images alone. In 2023, Catherine Fries's team flagged 3 candidates in JWST's data that could potentially be dark stars. These objects had been classified as early galaxies, but their brightness and color profiles matched what dark star theory predicted. However, photometry, measuring how bright something is and what color it appears, can only take you so far. It can't reveal the true nature of an object. For that, astronomers need spectroscopy, which splits the light into its component wavelengths and reveals the chemical fingerprints within. If photometry is like looking at a person's face, spectroscopy is like running a blood test. At the time, no one had the spectroscopic data needed to confirm or rule out the dark star hypothesis for those candidates. They could be galaxies, or they could be something entirely new. The distinction was crucial. If even a fraction of JWST's most distant galaxies turned out to be individual dark stars, our entire census of the early universe would need to be rewritten. The number of galaxies at high redshift would drop, star formation rates would change, and the impossible masses that started the whole crisis might partially dissolve, because some of those bright dots weren't collections of stars at all, but single objects burning a fuel that physics has never directly observed. Spectroscopy was the only way forward, and in October 2025, a surprising spectral feature appeared. The target was JWST 14-0, the most distant spectroscopically confirmed galaxy at the time, sitting at redshift 1432. Light from this object left its source when the universe was just 290 million years old. Stefano Carniani's team had already confirmed its redshift using about 10 hours of near-infrared spectrograph observations, and they had detected oxygen in its spectrum, a surprise in itself. But a separate analysis of the same data, published in October 2025, found something else: a tentative absorption feature at 1,640 angstroms, corresponding to helium. To understand why this matters, it helps to know what helium Cli is. Regular helium has 2 electrons. If you strip away one, you get singly ionized helium. Strip away both, and you get doubly ionized helium. Creating helium tellure requires extremely energetic photons, much more than what ordinary stars produce, especially in the early universe. In the modern cosmos, you find helium sui emission near the most violent objects: quasars, Wolf-Rayet stars, and active galactic nuclei. But at redshift 14, just 290 million years after the Big Bang, none of those sources should exist yet. The first stars at this epoch should have been mostly hydrogen-burning, incapable of producing the hard ultraviolet radiation needed to doubly ionize helium. And yet, there it was, a dip in the spectrum at exactly 1,640 angstroms. The dark star model predicts precisely this signature. The extreme temperatures generated by dark matter annihilation inside a supermassive dark star would naturally produce the hard ultraviolet radiation needed to ionize helium twice over. A dark star of several 100,000 solar masses would show helium tellure absorption at this wavelength. The signal was tentative. The signal-to-noise ratio hovered around 2, which in astronomy means you can see it, but you wouldn't bet your career on it. A signal-to-noise of 5 is the traditional threshold for a confirmed detection. It could be real, it could be an artifact of the data reduction process, or it could just be noise that happens to land at an interesting wavelength. But if it's real, the consequences would ripple through multiple fields at once. It would mean the most distant confirmed object in the universe isn't a galaxy. It's a single star powered by a substance that's never been directly detected. It would be the first observational evidence that dark matter interacts with visible matter in a way that produces light. It would also mean that an unknown number of other bright, compact, high redshift objects in JWST's data might be dark stars misidentified as galaxies. The early universe's population census could be fundamentally wrong. We assumed we knew what we were looking at, but confirmation would require deeper spectroscopy, more integration time on the same object, or observations of other dark star candidates. JWST has the capability, but telescope time is precious and highly competitive. So, the tentative detection sits in the literature, a whisper at 1,640 angstroms. While astronomers debated whether JWST 4 might be a dark star, another spectroscopic analysis of a different object was revealing a chemistry problem that had no easy solution. GN-Z11, sitting at redshift 10.6, had previously held the record as the most distant galaxy ever observed. Detected first by the Hubble Space Telescope in 2016, JWST turned its powerful instruments on GN-Z11 in 2023. Roberto Maiolino's team at Cambridge used the near-infrared spectrograph to analyze its light with unprecedented precision. What they found was nitrogen, specifically a ratio of nitrogen to oxygen 4 times higher than what's measured in our own sun. This might sound like a technical detail, but it has big implications. Nitrogen in such amounts can't be produced quickly. According to standard chemical evolution models, you need intermediate, mass stars to live out their full lifetimes. These stars burn hydrogen, then helium, and eventually produce nitrogen through the carbon-nitrogen-oxygen cycle in their cores. When they die, they expel that nitrogen into the surrounding gas, which the next generation of stars incorporates. The nitrogen to oxygen ratio builds up gradually over hundreds of millions to billions of years. But 430 million years isn't enough time. The universe at that age hadn't existed long enough for multiple generations of intermediate, mass stars to live, die, enrich the gas, and build up nitrogen to 4 times the solar ratio. The math just doesn't close. Maiolino's team proposed an alternative: supermassive stars. Not the dark stars powered by dark matter, but a different class of theoretical object. These would be stars between 1,000 and 100,000 solar masses, formed through runaway collisions in extremely dense stellar clusters. In such environments, young stars are packed so closely together that gravitational interactions cause them to merge repeatedly, building up objects of extraordinary mass in just a few million years. These supermassive stars would burn hot and fast, producing nitrogen-rich winds throughout their short lives. A supermassive star of 10,000 solar masses could enrich its surroundings with nitrogen in about 1 million years, fast enough to explain JWST chemistry. But there's a catch: these conditions are extreme, and no simulation has fully reproduced them. The stellar densities required for runaway collisions are far beyond anything observed in the modern universe. And supermassive stars of this type have never been directly detected. They remain theoretical, invoked because the data demands them, not because anyone has seen one. The nitrogen problem in JWST wasn't alone. JWST 14 already had oxygen at 290 million years. Now JWST had nitrogen at 430 million years. 2 different elements, 2 different objects, 2 different epochs, both demanding chemical enrichment that outpaces every standard model. Each of these chemical discoveries, oxygen in JWST 14 and nitrogen in JWST, could have been dismissed as isolated oddities, perhaps the result of some rare, unmodeled process or even a fluke in the data. But then a third chemical anomaly appeared, turning a pair of outliers into a pattern that couldn't be ignored. This time, the focus was on polycyclic aromatic hydrocarbons, or PHs. These are large, complex molecules made of interlocking rings of carbon and hydrogen atoms. On Earth, you encounter PHs in everything from grilled food to car exhaust. In space, they're everywhere, filling the gaps between stars, coating meteorites, and showing up in the spectra of the interstellar medium throughout the Milky Way. Astronomers know how PHs forms. They're produced by carbon-rich stars in the late stages of their evolution, specifically during the asymptotic giant branch phase. As these stars shed their outer layers, carbon atoms bond into increasingly complex structures, eventually forming PHs. But this process takes time. AGB stars are not young, they're intermediate, mass stars nearing the end of their lives, and it takes at least 100 million years, often much longer, for a star to reach this stage. For a galaxy to develop a detectable patch signature, you need not only the stars to evolve, but also for the molecules to accumulate in sufficient quantities to show up in observations. The conventional estimate was that it would take about 1 billion years of stellar evolution for a galaxy to build up enough PAs to be detectable. Then JWST detected PAs at redshift 6-7 when the universe was only about 900 million years old. That's barely within the theoretical minimum, and only if you assume the most optimistic conditions. Stars forming immediately after the Big Bang, evolving at the fastest possible rate, producing maximum carbon yields, and mixing efficiently into the surrounding gas. Even then, the numbers are tight. 900 million years is a razor-thin margin. Now, lay these three chemical findings side by side: oxygen at 290 million years in JWST 14, nitrogen at 430 million years in GN-Z11, and PATS at 900 million years at redshift 6.7. Three independent chemical signatures, detected in three different objects, at three different epochs by three different research teams. Each one, on its own, pushes the limits of what standard stellar evolution allows. Together, they tell a story that none of them could tell alone. The early universe's chemistry was mature almost from the start. Complex elements and molecules appeared in the first few 100 million years, as if the chemical clock had started running before the universe gave it permission. At this point, the problem was no longer just about how galaxies formed or how black holes grew. The chemistry of the early cosmos was off, too. Every timeline that cosmology relied on, for stars, for galaxies, for black holes, for dust, for molecules, was coming up short compared to what JWST was finding. And if the timeline was wrong for the objects inside the universe, it raised an obvious question about the biggest timeline measurement in all of cosmology: the rate at which the universe itself is expanding. That number, known as the Hubble constant, was already in trouble. The Hubble constant, named after Edwin Hubble, measures how fast the universe is expanding. Its units are kilometers per second per megaparsec for every megaparsec of distance. A galaxy moves a certain number of kilometers per second faster. Measuring this number should be straightforward, but for decades, different methods have given different answers. In the early 2000s, two main approaches emerged as the gold standard. The first is the local distance ladder, pioneered by Adam Rees and his team. They use Cepheid variable stars, stars that pulse with a period directly related to their intrinsic brightness, as distance markers. By measuring the pulse period, astronomers can calculate the true brightness, compare it to the observed brightness, and determine the distance. Calibrate enough Cepheids, then use them to calibrate type Ia supernovae at greater distances, and you can build a ladder that reaches across the observable universe. Rees's team consistently gets a value of about 73 kilometers per second per megaparsec. The second method skips the local universe entirely. The Planck satellite, operated by the European Space Agency from 2009 to 2013, mapped the cosmic microwave background, the afterglow of the Big Bang. By analyzing the precise pattern of temperature fluctuations in that radiation, physicists can extract a prediction for what the Hubble constant should be today, assuming the standard cosmological model is correct. So, 73 versus 67, 4 and 8% gap. For years, the assumption was that one of these measurements must have a systematic error. Maybe the Cepheid distances were off. Or maybe dust was dimming the light. Or perhaps stellar crowding in distant galaxies was skewing the measurements. The Hubble Space Telescope's resolution was limited, and in crowded fields, individual Cepheids could blend with neighboring stars, making them appear brighter and thus closer than they really were. JWST changed the game. Its infrared instruments and superior resolution could resolve individual Cepheids in galaxies where Hubble saw only blurs. Rees's team re-observed the same Cepheid fields with JWST and compared the results. The mean discrepancy between Hubble and JWST Cepheid measurements was just 0.3 magnitudes, 6 times smaller than what would be needed to explain the tension between 73 and 67.4. JWST confirmed the local measurement 72.6, plus or minus 20. The Hubble tension is real. It's not a calibration problem or instrument noise. Two of the most precise measurements in the history of physics, measuring the same quantity, disagree at a statistical significance of 5 sigma. And then, a massive instrument in the Arizona desert made things even more complicated. Wendy Friedman, a veteran in the field, leads the Carnegie Hubble program, which uses a different method, the tip of the red giant branch. Red giant stars, when they reach a specific phase of helium ignition, all achieve nearly the same peak luminosity, making them a standard candle like Cepheids but less sensitive to dust and crowding. Friedman's result lands somewhere between 69 and 72, right between Rius and Planck. On the surface, this should help narrow things down, but instead, it created a third camp. Each team stands by their method, each accuses the others of missing some subtle error, and the disagreement is not just scientific, it's personal. Careers, funding, and reputations are on the line, but behind the human drama, a deeper question lingers. What if none of the measurements are wrong? What if the model connecting them is broken? If all the measurements of the Hubble constant are correct within their own frameworks, but they still don't agree, then the problem might not be with the data, it might be with the model that connects the early universe to the present day. The standard cosmological model, known as lambda CDM, predicts a specific relationship between the expansion rate measured from the cosmic microwave background and the expansion rate we measure locally in the modern universe. If the model is right, those two numbers should match, but they don't. This disagreement, known as the Hubble tension, has become one of the most persistent puzzles in cosmology. For years, both sides dug in, refining their measurements and searching for hidden errors. JWST's confirmation of the local value only made the tension more acute. Planck's early universe value remained rock solid. The gap persisted. Then, in March 2024, a different kind of instrument added a new twist. The Dark Energy Spectroscopic Instrument, perched atop the Mayall telescope in Arizona, isn't a space telescope. It's a ground-based machine designed to map the three-dimensional positions of tens of millions of galaxies and quasars across 11 billion years of cosmic history. Its heart is a set of 5,000 robotic fiber optic positioners, each one able to target a different object in the sky. In a single exposure, DSI can collect the spectra of 5,000 galaxies at once. Over its planned 5-year survey, it aims to map about 40 million objects, building the most detailed map of the universe's expansion ever assembled. DSI measures something called the baryon acoustic oscillation signal. In the first few 100,000 years after the Big Bang, sound waves rippled through the hot plasma of the early universe. When the universe cooled and became transparent, those sound waves froze in place, leaving a characteristic spacing in the distribution of galaxies, a kind of cosmic yardstick. By measuring how this spacing appears at different redshifts, astronomers can track how the universe has expanded over time. In March 2024, DSI released its first-year results, based on about 6 million galaxies and quasars. When the team fit the data to the standard cosmological model, something unexpected popped out. The equation of state parameter for dark energy, labeled, came out as 0.52 plus or minus 0.57. In the standard lambda CDM model, this parameter should be exactly 1. That value means dark energy is a cosmological constant. It doesn't change. It has the same strength everywhere and at all times, from the beginning of the universe to its end. But DSI's result wasn't 1. The first-year data showed a 2.8 sigma deviation from the expected value. In physics, 2.8 sigma means there's about a 1 in 20 chance the result is just a random fluctuation. Interesting, but not conclusive. Most anomalies at this level fade away with more data. But by January 2026, after more of the survey had been processed, the signal had grown stronger. The latest analysis pushed the significance to 4.2 sigma. In particle physics, a 5 sigma result is the gold standard for a discovery, about a 1 in 3.5 million chance of being a fluke. DSI wasn't quite there yet, but it was close enough that the cosmology community couldn't ignore it. If dark energy isn't constant, if it's weakening over cosmic time, the consequences ripple through every model of the universe's past and future. the expansion history changes. The relationship between the early and late universe shifts. And, perhaps most intriguingly, it might connect to the other crisis that JWST has been documenting since 2022. In November 2025, a paper appeared that drew a line between the expanding universe and the impossible galaxies. The authors proposed something that had been whispered about in cosmology circles, but rarely stated outright. The anomalies JWST keeps finding in the early universe and the Hubble tension measured in the late universe might share a single cause. Here's the logic: if dark energy was stronger in the early universe than it is today, the expansion history between then and now would be different from what lambda CDM predicts. The early universe would have expanded at a different rate. The relationship between redshift and cosmic time would shift. An object observed at redshift 14 might not correspond to 290 million years after the Big Bang. It might correspond to a slightly different age, under slightly different conditions, with slightly different densities and temperatures. Even a small difference, compounded across every calculation that depends on the expansion history, could have a big impact. Galaxy masses inferred from luminosity depend on the assumed distance, which depends on the expansion history. Star formation rates depend on the time available. Black hole growth calculations depend on the time between the Big Bang and the observed epoch. Change the expansion history, and you change the denominator in every one of those calculations. The paper used D-size evolving dark energy parameters to construct an alternative expansion model, labeled UB-A-CDM. The authors recalculated predicted galaxy populations, star formation rates, and black hole growth timelines under these modified conditions. Several of the JWST anomalies that seemed impossible under lambda CDM became less severe, not fully resolved. But the gap between observation and prediction narrowed. The impossible became merely improbable. And the Hubble tension, under this same modified expansion history, also eased. The predicted early universe value for the Hubble constant shifted slightly, reducing the gap between the Planck measurement and the local measurement. Two separate crises, one in the early universe, observed by JWST, and one in the expansion rate, measured by competing teams, partially dissolved under the same modification to the same model. When a single change to a theory addresses multiple independent problems, it carries more weight than a patch that fixes only one. But elegance isn't proof. The modified model introduces new free parameters, and more free parameters make any model more flexible. Critics pointed this out immediately. You can always improve the fit by adding knobs to turn, but the question is whether those knobs correspond to real physics. DSI is still collecting data. Its full 5-year survey won't be complete until around 2026. Each additional year will either strengthen or weaken the 4-2 sigma signal. If it crosses 5 sigma with the full dataset, the case for evolving dark energy will be hard to dismiss. And if evolving dark energy truly connects the two biggest anomalies in modern cosmology, the standard model may need more than just patches. It may need a replacement. If dark energy is truly changing over time, the implications reach far beyond just the early universe or the present-day expansion rate. They touch on the ultimate fate of everything. For a quarter of a century, the prevailing view has been that the universe's expansion will continue to accelerate forever, driven by a cosmological constant, an unchanging form of dark energy. In this scenario, galaxies outside our local group will eventually recede so quickly that their light will be stretched beyond detectability. Over unimaginable timescales, the observable universe would shrink to just our local cluster, then to a single merged galaxy, and finally to isolated remnants cooling in an ever-expanding void. This is the so-called heat death scenario, not a dramatic end, but a slow fade into darkness and maximum entropy. Some versions of this scenario are even more extreme. If dark energy were to grow stronger over time, the acceleration could eventually tear apart galaxy clusters, then galaxies, then solar systems, and even atoms themselves, a hypothetical Big Rip where the expansion rate becomes infinite in a finite time. But DESA's data hints at the opposite. Dark energy may be weakening. If the equation of state parameter, W, is truly less negative than 1 and trending upward, then the acceleration won't last forever. At some point, gravity could begin to win again. The expansion would slow, then halt, and perhaps even reverse. The universe could begin to contract, slowly at first, then more rapidly. With galaxies falling back toward each other, background radiation heating up, and all structures eventually crushed together. This would be a Big Crunch, the reverse of the Big Bang. Of course, these are speculative extrapolations. The timescales involved are so vast that even small uncertainties in today's measurements balloon into enormous uncertainties about the far future. No scientist would bet their reputation on a specific timeline. But the direction matters. For decades, the assumption has been that the universe expands forever. Now, the data is nudging us to consider other possibilities. And all of this is happening while JWST continues to reveal that the early universe was far more complex and mature than anyone expected. The telescope's discoveries aren't just about distant galaxies or ancient black holes. They're about the very structure of the cosmos itself. Take, for example, the discovery of large-scale structures, groups and clusters of galaxies, forming billions of years ahead of schedule. After the initial shock of the impossible galaxies from the CER survey, astronomers recalibrated their data, corrected for overcounting, and revised their mass estimates downward. Critics declared victory, and headlines moved on. But even after all the corrections, the revised masses were still too high for the standard model to comfortably explain. In 2025, the Renaissance simulations, a suite of advanced computer models, tried to reproduce JWST's observations within the Lambda CDM framework. They introduced a top-heavy initial mass function, meaning that the first stars were predominantly massive, rather than following the distribution seen in the modern universe. This adjustment could reduce the inferred masses of early galaxies by about a factor of 10. Bringing some of them within the range allowed by the standard model. But this solution had a circular feel. The initial mass function has been measured locally and appears to be universal. Changing it just to save the model isn't independent evidence. It's a patch. And even with this adjustment, the corrected galaxy masses still sat at the upper edge of what Lambda CDM permits. The overcounting scandal made the problem quieter, and the Renaissance simulations made it more sophisticated, but neither made it disappear. This is a pattern that keeps repeating. Each anomaly generates a proposed fix, each fix works partially, but leaves a residual problem that accumulates alongside every other leftover from every other fix. One unexplained residual is a loose thread. 10 of them, all pointing in the same direction. That the early universe was more active and structured than the standard model allows, suggests something deeper. For a generation, astronomers told a simple story about the first billion years. The universe began as a hot, smooth soup of hydrogen and helium. Gravity slowly pulled gas into clumps, which became the first tiny, metal-poor proto-galaxies. Small things merged into bigger things over billions of years. Dust and metals were late arrivals. Structure was a late arrival. Everything built up gradually, like sediment layering on the ocean floor. But JWST found the ocean floor already covered. The sediment was already deep. In 2024, a new class of objects called red monsters appeared in the data. These are massive, dusty galaxies sitting inside the first billion years after the Big Bang, and they violate every part of the simple story at once. Each one is nearly the size of the Milky Way, with high dust content and star formation rates double those seen today. And dust is the key detail, because dust is made of metals, and metals are forged inside stars. For dust to exist, stars must live, burn through their fuel, explode, and scatter metals into the surrounding gas. That gas must cool, collapse, form new stars, and repeat the cycle, each generation taking hundreds of millions of years. The dust inside a red monster represents the accumulated output of multiple stellar generations, somehow completed within a window that should not have been long enough for even one. The standard story said the first billion years would produce small, fragile, metal-poor objects. Instead, JWST found fully operational galactic ecosystems, dust, metals, structure, and size, all present at once, all impossibly early. It's not that one measurement is off. Every measurement is off in the same direction. The early universe wasn't assembling slowly, it was already assembled. The discovery of these red monsters added a new dimension to the puzzle. While the earlier CERS galaxies were notable for their sheer mass, the red monsters were remarkable for their completeness. It's one thing for a galaxy to be massive, it's another for it to be chemically mature, dust-rich, and forming stars at a breakneck pace, all within the universe's first billion years. These galaxies didn't just have a lot of stars. They had already cycled through multiple generations of star birth and death, producing the dust and metals that are usually considered hallmarks of much older systems. This completeness is what set the red monsters apart. In the standard model, you might be able to explain away high stellar masses by tweaking the initial mass function, assuming the first stars were unusually massive and bright, so you'd need fewer of them to account for the observed light. But that trick doesn't work for dust. In fact, a top-heavy initial mass function would actually make the dust problem worse, not better. Massive stars burn hotter and faster, and their supernovae are so energetic that they tend to destroy dust grains rather than create them. So, the very patch that helps with the mass problem only deepens the mystery of the dust. Other proposed fixes, like bursty star formation, where galaxies form stars in intense, short-lived episodes, also fall short. While such bursts might help build up stellar mass quickly, they don't provide the sustained chemical enrichment needed to explain the amount of dust and metals seen in these early galaxies. Dust requires continuity, multiple generations of stars living, dying, and enriching the interstellar medium over time. A single burst just doesn't cut it. So, the early universe wasn't just making stars faster than expected. It was running a full-fledged chemical factory, cycling material through generation after generation at a pace that no known mechanism can reproduce. And if individual galaxies could achieve this, the next logical question was, could groups of galaxies do it too? The answer came from a survey that wasn't even looking for it. The JWST Advanced Deep Extragalactic Survey had been mapping the most distant galaxies in unprecedented detail. Among its targets was a region where galaxies appeared to cluster unusually close together at high redshift. Follow-up observations revealed something that forced astronomers to rethink the timeline for cosmic structure formation. JWST turned out to be a protocluster, not just a single galaxy, but a gravitationally bound group of at least 66 galaxies, all sitting at roughly 1 billion years after the Big Bang. X-ray observations detected hot gas between the member galaxies, with temperatures exceeding 1,000,000 degrees, a telltale sign of a mature intracluster medium. This kind of superheated gas forms when galaxies have been gravitationally interacting for extended periods, their halos colliding and shock, heating the intergalactic material. The previous record for a structure like this was at redshift 2, about 3 billion years after the Big Bang. JWST arrived 2 billion years ahead of schedule. Galaxy clusters are the largest gravitationally bound structures in the universe. The Virgo cluster, for example, contains over 1,000 galaxies and spans about 20 million light-years. These structures take enormous amounts of time to assemble, because they require galaxies to form first, then fall toward each other under gravity, and finally settle into a stable configuration. Each step is thought to take billions of years. Finding a protocluster with hot intracluster gas at just 1 billion years means every step in that sequence happened much faster than any simulation can reproduce. This is where the pattern becomes impossible to ignore. Individual galaxies are too massive. Black holes are too heavy. Chemistry is too mature. Star formation is too efficient. Hundreds of little red dots appear and vanish. And now, large-scale structures are forming billions of years too early. Each anomaly, taken alone, could be dismissed as a statistical fluke or a measurement error. But taken together, they all point in the same direction. The model that predicts when each of these things should appear is consistently off. And it's off in the same way every time. Everything is too early, too complete, too mature for the universe's age. The lambda CDM model was built to explain the large-scale structure of the universe. Its predictions for the cosmic microwave background are stunningly accurate. Its description of the cosmic web at low redshift matches observations beautifully. By almost any measure, it's one of the most successful models in the history of science. But it cannot produce what JWST sees in the first billion years. Not the galaxies, not the black holes, not the chemistry, not the clusters. Some of these anomalies might yield to clever modifications. The Renaissance simulations showed that a top-heavy initial mass function can reduce inferred galaxy masses by about a factor of 10. That helps with one problem, but it doesn't help with dust, clusters, black hole masses, the little red dots, the chemical enrichment timeline, or the star formation efficiency. Each patch fixes one leak and ignores the others. But before we even get to the question of whether lambda CDM can survive, there's a more immediate puzzle. The universe's transition from an opaque fog to transparent space during its first billion years, a process called reionization. Astronomers thought they understood how it worked. JWST proved they didn't. Reionization is one of the great phase transitions in cosmic history. For the first few 100 million years after the Big Bang, the universe was filled with neutral hydrogen, making it opaque to light. Then, the first luminous objects began producing ultraviolet photons, ionizing the surrounding hydrogen and clearing bubbles of transparency that gradually merged until the entire universe became see-through. The textbook timeline placed the end of this process at redshift 6, about 1 billion years after the Big Bang. But JWST found that reionization ended earlier than models predicted, closer to redshift 9, or about 550 million years after the Big Bang. That's not a small shift. Moving the endpoint by 450 million years means there were far more ionizing photons, far earlier, than any known source can account for. This is the photon budget crisis. Add up every galaxy, every quasar, every active galactic nucleus, even the little red dots, and the total number of ionizing photons still falls short of what was needed to clear the fog by redshift 9. Something was producing ultraviolet radiation in the early universe that hasn't been identified. It's either invisible to current instruments or belongs to a category of objects that hasn't been theorized. Dark stars could fill the gap, if Catherine Freese's model is correct. Supermassive dark stars powered by dark matter annihilation would have been extraordinarily luminous in ultraviolet. A single dark star of 1 million solar masses could produce as many ionizing photons as an entire dwarf galaxy. If dark stars were common, they would be precisely the missing source the photon budget needs, and their disappearance would explain why no local counterpart exists. The photon budget crisis ties together nearly every other anomaly JWST has uncovered. If there were more luminous sources in the early universe than current models account for, those same sources would contribute to the unexplained brightness that makes early galaxies appear so massive. Some fraction of the impossible stellar mass might not be stars at all. It could be the light from objects that aren't galaxies, but something else entirely, counted as galaxies simply because astronomers didn't know to look for anything different. This is the thread that weaves through the entire investigation: the over-massive galaxies, the outsized black holes, the mature chemistry, the early clusters, the little red dots, and the photon budget crisis. They're not isolated problems. They're symptoms of a deeper issue. Our census of the early universe is incomplete. JWST is finding things that were never in the inventory, and the total energy output of the early universe exceeds what every object in that inventory can produce. The problem isn't just with individual predictions, it's with the model itself, which seems to be missing something fundamental. Let's step back and take stock of what JWST, DESI, and Chandra have collectively revealed in just 3 years. Galaxies 10 to 100 times more massive than any model predicted, sitting at redshifts above 10 within the first 500 million years. These findings have been confirmed across multiple surveys, and even after recalibration, remain too massive for the standard model. A supermassive black hole at 470 million years that weighs as much as every star in its host galaxy, a mass ratio 100 to 1,000 times higher than any black hole in the local universe. This was detected through gravitational lensing and weeks of Chandra X-ray observation. Oxygen at 290 million years, nitrogen at 430 million years, and polycyclic aromatic hydrocarbons at 900 million years. These are 3 independent chemical signatures, each requiring timescales the universe hadn't yet provided. Star formation efficiency above 50% in blue monsters, compared to a universal average of 10%. Some early estimates from CRs even approached 100%. No known feedback mechanism allows this. 341 little red dots between redshifts 5 and 10, matching no known astronomical object, with active galactic nucleus densities 50 times higher than predicted. One of them, the Cliff, produces a Balmer break that fits no existing template. The entire population vanished without leaving descendants. A tentative helium absorption line at 160-40 angstroms in JWST GSCOT no. Consistent with a supermassive dark star powered by dark matter annihilation. The signal-to-noise ratio is about 2, not proof, but a whisper. The Hubble tension confirmed as real by JWST, with local measurements at 73 pc and cosmic microwave background measurements at 67.4. That's an 8% gap at 5 sigma significance, not caused by instrument error. Dark energy showing signs of weakening over cosmic time, with DESI measuring the equation of state parameter at 0.752 instead of 1, now at 4.2 sigma significance and approaching the 5 sigma discovery threshold. A protocluster of 66 or more galaxies with million-degree intracluster gas at 1 billion years. 2 billion years before any simulation predicted such a structure could exist. More ionizing photons in the early universe than every known source combined can produce. There's an unidentified contributor to reionization that cleared the cosmic fog earlier than any model accounts for. 10 independent anomalies, discovered by different teams, using different instruments, across different redshifts. Each one challenges a specific prediction of the lambda CDM model. Together, they describe a universe that was far more complex, energetic, and structured in its first billion years than the reigning model of cosmology allows. Any one of these could be a fluke. Any two might be coincidence. But 10, all pointing in the same direction, all saying the early universe was more advanced than predicted, is a pattern. And the question this pattern raises isn't just about galaxies or black holes or chemistry. It's about whether the model that has governed cosmology for a generation can survive what JWST has found. Of course, lambda CDM has its defenders, and their arguments are not trivial. The model has been the backbone of cosmology since the late 1990s. It describes a universe made of about 5% ordinary matter, 27% dark matter, and 68% dark energy, expanding from a hot initial state, according to general relativity. Its predictions for the cosmic microwave background are stunningly accurate. Its description of the cosmic web at low redshift matches observations beautifully. It even predicted the accelerating expansion of the universe before supernova confirmed it. By almost any measure, lambda CDM is one of the most successful physical models ever constructed. But that success is also its vulnerability. An entire generation of cosmologists has built their careers on it. Grants, tenure, and textbooks are all tied to its framework. Declaring a crisis in the foundational model of your field isn't just a scientific act, it's a personal and professional risk. The resistance to abandoning lambda CDM isn't irrational, it's human. And the resistance has produced real results. The Renaissance simulations published in 2025 showed that incorporating top, heavy initial mass functions into lambda CDM can reduce the inferred stellar masses of early galaxies by about a factor of 10. This means some of the most headline-grabbing claims from 2023 were genuinely overcounted. The corrections brought some objects back within lambda CDM's tolerance. The overcounting scandal was real, and it damaged the credibility of the crisis narrative. But it didn't make the crisis disappear. The corrected masses are still too high. The correction made the problem less dramatic, but it didn't make it go away. It made it quieter, and quieter problems in science are dangerous because they stop receiving attention while continuing to exist. The quieter the crisis became, the more it risked being swept under the rug. Yet, the underlying issues persisted, quietly accumulating in the background of every new discovery. Each proposed fix, whether it was a top, heavy initial mass function, bursty star formation, or early dark energy, addressed only a single symptom. None could resolve the full suite of anomalies JWST and other observatories had uncovered. No single tweak to lambda CDM has yet been able to explain all 10 of the major discrepancies at once. And then there's the class of objects that resists every patch entirely, the little red dots. When these compact, high redshift sources first appeared in JWST's data, astronomers cataloged them as small, distant galaxies, unremarkable except for their numbers. But as spectroscopic follow-up continued, it became clear they were anything but ordinary. Their active galactic nucleus densities were 50 times higher than any model predicted. Their spectra didn't match any known galaxy, quasar. The cliff in one of their spectra produced a Balmer break that sits in a region of parameter space where no theoretical model applies. And, most strikingly, the population is bounded in time. They appear around redshift 10, cluster densely between redshifts 5 and 8, and then vanish completely below redshift 5. No known astronomical population behaves this way. Galaxies evolve, merge, and change, but they leave descendants. The little red dots do not. Joel Lage's black hole star hypothesis offers the most coherent explanation so far. If these objects are direct, collapsed black holes wrapped in heated gas cocoons, their disappearance is natural. The cocoon phase is temporary. Dark matter and primordial gas funnel onto the collapsing object, heating the surrounding envelope to temperatures that produce emission mimicking a stellar population. From the outside, through JWST's eyes, it looks like a compact galaxy, but it's actually a single object, a massive black hole inside a glowing shell. When the gas is consumed or blown away, the cocoon fades, leaving behind a naked supermassive black hole, invisible at optical and near-infrared wavelengths. The little red dot didn't evolve into something else, it shed its skin. The chrysalis dissolved, leaving only the black hole at the center, which then became the seed around which a galaxy eventually formed. If this is correct, it flips the standard relationship between black holes and galaxies. Traditionally, galaxies form first, and black holes grow inside them. In Leje's model, black holes form first, wrapped in a brief, visible cocoon, and galaxies crystallize around them later. The little red dots weren't a type of galaxy. They were the embryonic phase of supermassive black holes, visible for a cosmic instant and then gone. This would explain UHZ-1, the galaxy with a black hole as massive as all its stars combined. If the black hole came first and the galaxy was still catching up, the mass ratio would make sense. It would also explain the mature chemistry, since the cocoon phase would involve intense radiation processing gas at extreme temperatures. And it would explain why these objects vanish. Over billions of years, galaxies grow around the seeds, burying the evidence of the cocoon phase beneath layers of ordinary stellar evolution. If each little red dot became the core of a galaxy, then the supermassive black holes at the centers of galaxies across the observable universe may all trace their origin to a brief, violent phase that nobody knew to look for until JWST pointed its mirror at the deep past. The phrase, "beyond the Big Bang," has appeared in headlines since JWST's first anomalies surfaced. It doesn't mean before the Big Bang, at least not in the traditional sense. What it really means is that JWST is finding things that the standard Big Bang model cannot produce. If you run the clock forward from the initial singularity, through nucleosynthesis, recombination, and the Dark Ages, you simply can't arrive at what JWST observes at 290 million years. The physics doesn't connect point A to point B. The model that starts with the Big Bang and runs forward falls short. In that sense, the observations are beyond what the Big Bang framework can explain, but the data has pushed the conversation even further. JWST already contains oxygen at 290 million years. Oxygen requires at least one full stellar generation to form. A massive star must ignite, burn through hydrogen and helium, fuse carbon and oxygen in its core, and explode as a supernova to scatter those elements into the surrounding gas. The fastest massive stars can complete this cycle in about 2 to 3 million years, but they need to form first, and before that, gas must cool and collapse, which takes additional time. The most aggressive models place the first stars at about 100 million years after the Big Bang. That leaves 190 million years for a star to form, live, die, enrich its surroundings, and for a new generation to incorporate that enriched material into a detectable galaxy. It's possible, barely, but the nitrogen in GNZ11 at 4 to 30 million years is even harder to explain. A nitrogen to oxygen ratio 4 times solar requires not one but multiple stellar generations, or supermassive stars of 1,000 to 100,000 solar masses that themselves need extreme conditions to form, and the PIAS at 900 million years require sustained chemical processing across generations of AGB stars. Each observation pushes the required starting conditions further back. If the chemical maturity JWST observes demands processes that need hundreds of millions of years to complete, and those processes must have already finished within the first few 100 million years, then the processes may have started before the epoch we can observe, possibly before the Big Bang itself. This used to be the realm of philosophy. Some theorists, like Roger Penrose, have proposed cyclic cosmologies, where our Big Bang is just the latest in an infinite series of cosmic cycles. Others have suggested bouncing universes or higher, dimensional collisions. These ideas were once mathematical curiosities, elegant but untestable. JWST hasn't proven any of them correct, but it has produced observations that seem to demand conditions prior to the standard starting point. The first few 100 million years were not simple. They were not a blank slate of hydrogen and helium slowly assembling. They were complex from the start, and complexity at the start implies conditions that produced it, which implies something came before. The possibility that the universe's earliest moments were already complex, and that something fundamental is missing from our models, is both unsettling and exhilarating. The hints from JWST, Desai, and Chandra are not just isolated puzzles. They're clues that the story of the cosmos may be far richer and stranger than we imagined. Consider the tentative detection of the helium-2 absorption line at 160-40 angstroms in JWST 14.0. If this signal is real, it would be the first direct evidence that dark matter does more than just exert gravitational pull. It might actually interact with ordinary matter in a way that produces light. Catherine Freese's dark star model predicts exactly this kind of signature dark matter particles annihilating inside a primordial gas cloud, heating it to extreme temperatures and preventing it from collapsing into a normal star. Instead, the cloud swells into a supermassive dark star, potentially reaching 1 million solar masses, shining with the luminosity of an entire galaxy. The helium I line is a predicted fingerprint of this process, requiring temperatures that only dark matter annihilation, or the most extreme stellar populations, could produce in the early universe. But the signal is faint, with a signal-to-noise ratio of about 2. In astronomy, that's not enough to claim a discovery. It's a hint, a direction to look. Confirmation would require deeper spectroscopic observations, ideally of multiple candidates with much higher signal-to-noise. If confirmed, it would mean the most distant spectroscopically confirmed object in the universe isn't a galaxy, but a single star powered by a substance we've never directly detected. That would force a fundamental revision of our census of the early universe. Every bright, compact source at extreme redshift would need to be re-examined as a potential dark star. Some of the impossible galaxy masses might dissolve, because those bright dots aren't collections of billions of stars. They're individual objects producing galaxy-scale luminosity through a mechanism that wasn't in any model before JWST. Dark stars could also help solve the photon budget crisis. A supermassive dark star would be an extraordinarily powerful source of ionizing ultraviolet radiation. If dark stars were common in the first few 100 million years, they could provide exactly the missing photons needed to clear the cosmic fog during reionization. Their disappearance would explain why no local counterparts exist today. The sequence is suggestive. Dark stars form, shine briefly, exhaust their dark matter fuel, and collapse into massive black hole seeds. Wrap that seed in accreting gas, and you have something that looks like a little red dot. The cocoon phase ends, the black hole remains, and over billions of years, a galaxy grows around it. But all of this remains hypothetical until more data arrives. JWST is scheduled to revisit JWST 14.0 with deeper spectroscopy in its next observing cycle. If the helium I line strengthens above 5 sigma, the most distant object in the known universe could be a single dark star, and dark matter would have revealed a new side of itself. If the line fades into noise, the search will move to other candidates. Either way, the telescope will keep pointing at the places where our understanding breaks down, collecting photons from an era that refuses to fit the story we wrote for it. Meanwhile, the next generation of ground-based telescopes is preparing to join the search. The extremely large telescope in Chile, with its 39-meter mirror, will be able to resolve individual stars in distant galaxies that JWST can only see as smudges. The 30-meter telescope and the giant Magellan telescope will add complementary capabilities, each with their own unique instruments. Together, these observatories will be able to take spectra of the little red dots at resolutions high enough to distinguish between a compact galaxy, a black hole cocoon, or a dark star. They'll measure the helium I line with enough precision to confirm or rule out dark matter annihilation as a power source. They'll resolve the stellar populations inside red monsters, counting the chemical generations and determining whether the enrichment timeline is truly impossible or just implausible. The central question that started this investigation remains unanswered. Why does the early universe look nothing like our models predicted? 3 years of JWST data haven't brought us closer to a solution. They've only deepened the mystery. Each new observation raises new questions. Each proposed explanation introduces new tensions. The map of what we know has barely changed, but the map of what we don't know has expanded in every direction. Lambda CDM may survive. It has weathered challenges before. Dark matter was added when galaxy rotation curves didn't match expectations. Dark energy was introduced when the universe's expansion was found to be accelerating. The model has absorbed anomalies that would have toppled a less flexible framework. It could absorb these new findings too, by adding heavy mass functions, modified feedback, early dark energy, or heavy seed black holes. Each patch covers a portion of the problem. Perhaps enough patches will hold. Or perhaps the patches themselves are a sign that the model is reaching its limits. Maybe what JWST has found is the outline of something else entirely. A universe that was complex and chemically mature from nearly the beginning, for reasons our current framework can't accommodate. The next observation could change everything. The next spectrum, the next faint signal, the next unexpected pattern in the data could force us to rewrite the story of cosmic origins. For now, the universe is keeping its secrets. But with every photon JWST collects, with every new survey from DESI, with every spectrum from the next generation of telescopes, we're getting closer to the truth. The cosmos is stranger, faster, and more creative than we ever imagined. And the adventure of discovery is only just beginning.